All right, let's talk mixed Nash equilibrium. Um, it is, in particular, we're talking about zero-sum mixed Nash equilibria because they make a little bit more conceptual sense, even though the mechanics of it are very similar to non-zero-sum games. It's going to make a lot more sense with zero-sum games, I think. So, two assumptions you have to make for this. Your opponent is smart, and they're going to figure out your strategy, and if it has a weakness, they will exploit that weakness. They will take advantage of you. Okay? You can't assume they're going to be dumb. All right? And both players are capable of doing things random-ish. And when I say random-ish, I don't mean like random, fully random, like 50-50 each way, or if you only have two options. I mean, like if if you're supposed to do one thing 70% of the time, the other thing 30% of the time, you actually do that approximately right. Okay. But the main one there is that if your opponent is smart and will figure out your strategy. Okay. All right. So a few more things here. My glasses. Um, in a zero-sum game, you want to minimize your opponent's success, right? Because that maximizes your anything they lose, you gain. So you want to minimize their success. However, you've got to assume that they're going to try and maximize their success, right? So if you do something dumb, you can't be like, oh, well, they might mess up and screw up and like not take advantage of it, right? This is the same idea. They're going to try and maximize that. So you want to minimize their maximum. That's the goal. Okay? And the way to do that is to find out when your opponent's indifferent, when they can't be like, sometimes they're going to be like, in some situations, if you play, let's say your options are A and B, they might be like, well, if you play A, I'm going to play C. C is way better. Okay? And if you play D, or if you play B, they're going to play D because D is way better for them. What you want to make it is you want them to basically be like, I don't know, C and D kind of give me the same outcome, right? And that also has to do with best response, right? You want their best response to be, they can't, or sorry, Nash equilibrium, not best. You want them to be playing, right? You want them to be indifferent, right? Because the whole idea of Nash equilibrium is, right, so neither player wants to change their outcome and make it better, right? So that's what we want to do here. Okay, so let me give you an example of how to do it. So this is a pretty simple. It's actually from CS:GO. Not a game I played very much, but basically I should have had one more column on this, but I don't. This is the defense, the CT, and this is the offense or T side. Okay. And basically, the defense can stack a stack a defensive position or split. The T could go slow and rush. This is a very, very rudimentary example of a game, but right, this is approximately how it is. Okay, so the way I'm going to do this is the first thing I want to do is I want to figure out what mixture the offense is going to play. Okay, so in order to do that, the offense needs to make their opponent indifferent. So the defense has to be indifferent. So in order to do that, I'm going to say P is equal to the percent that the offense plays slow, and 1 minus P is the percent they rush. Right? Hope that makes sense. Those two things add up to 1, gives us a total like 100%, right? And then I'm going to do the defense's payoff. So this is for if I want to find the offense's strategy, I'm going to do the defense's payoffs. So what is the defense's payoffs for stacking? So if they stack, the payoffs are 2 times the probability of P times P plus 6 times 1 minus P. Again, that's the probability. It's because they get 2 if the offense plays slow and 6 if the offense plays rush. And if they split, it's equal to 7 times P plus 4 times 1 minus P. Right? Okay. So, I want to make them indifferent between those two choices. So what I do, I set those two formulas equal, or those two equations equal to each other. So I've got 2P plus 6 minus 6P equals 7P plus 4 minus 4P. Okay. Put it all on one side, we get 2 is equal to 7p, or p equals 2/7. Okay. That means at the Nash equilibrium, okay, the offense is going to be playing, playing slow 2/7 of the time, and rushing 5/7 of the time. Okay. Now we can also predict the defense's payoffs by plugging that in. So defense's payoffs, or expected payoff, is what would happen if I plug 2/7 into either of these equations. We set them equal to each other, so it could be either one. So we would have 2 times 2/7 plus 6 times 1 minus 2/7. All right. And if we do that, you get 34/7. Or in other words, the defense is averaging almost exactly half. Like they're just under half the time they win, essentially. Okay. But in order to do that, they have to play a heavily. The offense plays much more slow, and the defense plays much less slow and much more rush. Now, what about for the defense? What strategy should they use? Okay. Well, so if I want to figure out the defense's strategy, I'm going to use Q as percent stack, and 1 minus Q as percent split. Okay. All right. And then we do offense's payoffs. Again, we want the opposite. If we want to figure out defense's strategy, we have to figure out the offense's payoffs. So they get 8. So if the offense goes slow, they get 8 times Q plus 3 times 1 minus Q. And if they rush, they get 4 times Q plus 6 times 1 minus Q. Set those equal to each other. We have 8Q plus 3 minus 3Q equals 4Q plus 6 minus 6Q. Set that all equal, or add it all up, we get 5Q on this side, 3, we get minus 2, so we get 7Q equals 3. So Q equals 3/7. Okay. All right, and then we can get the payoff. The offense's payoff is going to be 8 times 3/7 plus 3 times 1 minus 3/7. And we actually didn't need to do this because this is going to come out to be 36/7, which we should have expected, because the 36/7 was 34/7. These two numbers have to add up to 10 because that's a constant sum game. So the offense in this particular game, the offense has a very slight advantage at the Nash equilibrium, very slight. All right, let's examine what's going on here. Okay, so the defense is stacking, right? They're going 8, 3, 4, or the defense is going to play heavily, or is going to be split evenly about between the two. Okay, which is interesting because for the defense, 2-6 versus 7-4, you would think 7-4 is way better, right? If I had a choice between going for something that could be a 2 or a 6 or a 7 or a 4, I'd go this way. And for the offense, it actually turns out that 8-3 is might be better than 4-6. But here's the thing: you have to make the opponent indifferent. So the offense plays rush because the defense wants to play split a lot. The offense plays rush more. Right? The offense plays rush a lot. They play this 5/7. Okay? And that's because they know the defense is better off playing split in general. So they play 5/7 to try to take advantage of that. And in return, the defense tries to split theirs more evenly because they know the offense is going to play rush a lot more. Okay, so it doesn't always end up that the player that has the advantage, that the obvious choice is played that much more because the other team is taking that into account. All right. What if we switch it up? What if and this doesn't make sense in terms of my original example, but what if the offense gets worse, the defense gets better at stacking? I don't know. I don't know how that would happen, but let's say they get better at stacking. Okay. So let's say this goes to, I don't know. What do you think? 6-4. Let's say this goes to 6-4. No, it's even better. 5-5. Let's go 5-5. Okay. We can do the same calculations here, right? We're still going to have, for the offense mix, we get that P is still percent slow, 1 minus P is still percent rush, right? So the defense's payoffs are 5 P plus 6 times 1 minus P. This is if they stack. That's going to be equal to, right, if they split, it's going to be 7P plus 4 times 1 minus P. Okay, let's see how this works out here. This is going to be 6 minus P equals 3P plus 4. This is 2 equals 4P. Now P is 1/2. So now they're going 1/2, 1/2. Okay. All right. The offense, or the defense, now if we want to figure the defense's mix, okay, we would do, right, Q is stack, 1 minus Q is split. Offense's payoff, if O is slow, we get 5 times Q plus 3 times 1 minus Q. And we set the equal to if O rushes, we get 4 times Q plus 6 times 1 minus Q. This is, right, 2Q plus 3 equals 6 minus 2Q, 4Q equals 3, Q equals 3 over 4. So now they're playing 3 over 4 and 1 over 4. Huh? All right, so we can then get the payoffs, right? And the payoffs are, if we put 1/2 into either of these things, this is 6 minus P, right? So the defense's payoff equals 5.5, which means the offense's will equal 4.5. So not surprisingly, the defense getting better made their expected payoff higher. Okay, that shouldn't surprise anybody, right? But what's interesting here is the shift in how the offense plays, right? In the previous example, the offense played 2/7 slow, and that gave them an option of 8 or 3. Now they're actually playing 5-3, so they actually got worse at playing slow, mostly because the defense got better. Let's say they got worse at playing this way, right? But they actually played it more. Now think about the opposite direction. What if this was the starting out? It was 5-5, 3-7, 4-6, 6-4. And what if we said instead the offense got better at slow playing, 8-2? It actually turns out they would have been, by getting better at playing slow, they actually would have played slow less. That happens sometimes. Sometimes by getting better, you don't have to use it as much. All right, because the other team is so worried about it, they defend against it and leave other areas open. All right, we're gonna do one more example, and then we're gonna be done here. Okay. All right, this is a football. This is the football one, right? So again, we want an offense. They can run or pass. So in other words, to find O's mix, right, we can do P equals percent run, 1 minus P. It's not at all what I should have been writing. 1 minus P equals percent pass. Okay, so then D's mix is if they do a run D, right, they're going to get -2 times P minus 8 times 1 minus P. And we're going to set that equal to, if they are past D, right, if they have a past D, it's going to be negative 5P minus 3 times 1 minus P. We can add it all up. Right, so we've got 8, 6, this is 6P minus 8 equals negative 3 minus 2P. 8P equals 5. P equals 5/8. Yep, that's right. And the expected payoff, for the defense, for the D, is 5/8. We plug that into this right here, times 8 minus 6, 630 over 8 minus 8. It's negative 34 over 8, which is negative 4.25. Okay, so this is the offense. The defense, no, sorry, the offense's mixture is going to be run 5/8, pass 3/8. All right, what about for the defense's mixture? Q equals percent run D, 1 minus Q equals percent pass D. So again, we do it, we set it up. So if for O, this should be D's payoffs. O's payoffs, right? They're going to go 2 times Q plus 5 times 1 minus Q. And we can set that equal to, this is if they run. And if they pass, it's going to be 8 times Q plus 3 times 1 minus Q. Okay. This is 5 minus 3Q equals 3 plus 5Q. 2 equals 8Q. Q equals 1/4. So we're going to play the run defense 1/4, which makes this the pass defense 3/4. Now it makes more sense why they're going to run more, right? If the D is mostly playing pass defense, right, then that explains why the offense is going to run more. All right, and the expected payoff is, guess what? 4.25, right? It's a zero-sum game. Okay, that's it. I guess the Nash equilibrium, if you actually want to describe the Nash equilibrium is the offense is 5/8, 3/8, and the defense is 1/4, 3/4. That's the Nash equilibrium. Okay. All right, that's it.